Hello, Pre-P Chemistry. How are we doing today? Mr. Oglesby here. So today we are going to be starting our next unit on Unit 9, which is going to be over chemical equations. And this lesson today is going to be over balancing chemical equations. So for this, first off, the basics. First off, we know that when a chemical reaction occurs, chemical bonds are broken and new bonds are going to form. So anytime we've got a chemical reaction, we are going to see chemical bonds being broken and formed as a result of that reaction. Now, we will see either energy is going to be produced as a part of that reaction or absorbed as a part of that reaction. And that's where we talk about endo and exothermic reactions. As a result of a chemical reaction, we do also see new compounds being formed. And so we can actually take those compounds and break them down, or take those compounds and put them together and build them up. And then the last thing that we do need to keep in mind with the basics for balancing chemical equations is that the law of conservation of mass is always followed. Okay? And so what I mean by that is that if I start with a certain mass, I need to end with that same mass. So let's take a look at that. So it says when 50 milliliters of isopropyl alcohol, which has a mass of 39.5 grams, is added to 50 milliliters of water, which has a mass of 50 grams, the mixture will have a volume of 98 milliliters. What is the mass in grams of this mixture? Now, first off, we do end up throwing this right here, this 98 milliliters in there as kind of a distraction for you. We know that when we actually add two different volumes together, even if they are 50 and 50, we might not get 100 milliliters. Why? Because those molecules can actually slide in between one another. And so because of that, we can actually have a volume that is less than what we started with. But the mass should stay the same. So what I mean by that is, I know that I had 39.5 grams that came from the isopropyl alcohol, and I know that I also had 50 grams that came from the water. So my total mass is going to be 89.5 grams. Okay, and so we do still need to follow the law of conservation of mass, which just says if you start with 89.5 grams, you should end with 89.5 grams. Okay? All right. Now, before we can actually start and talk about balancing equations, you do need to know some symbols as a part of these chemical reactions, okay? And so we're going to go through this and just kind of talk about what these symbols look like, what they mean, just so that you know when we're interpreting a chemical equation what's actually going on. So the first symbol we're going to talk about is called the yield symbol. So yield means to produce. So the symbol that we use for yield is just an arrow, and it's going to be pointing from the reactants to the products, okay? And so reactants to products. Remember that your reactant is going to be the thing that you start with, and the product is going to be the thing that is produced. It is the thing that you end with. Now, some reactions are what we call reversible reactions. And a reversible reaction, we signify that by saying we've got an arrow that goes one way, but it can also come back and go the other way. And what that tells me is that this reaction, when it occurs, we could produce those products, but those products could then turn around and produce those reactants. And so that's what we call a reversible reaction. Now, we also sometimes need to signify what is the state of matter in a chemical reaction. And the state of matter actually does affect what are the results of a chemical reaction. And so we do need to keep that in mind. When we represent what we call a solid or a precipitate, which is an insoluble solid formed by mixing two aqueous solutions. But if I take that, then I would symbolize this by putting in parentheses S. Okay? For gas, what do you think it would be? In parentheses, G. How about liquid? In parentheses, L. All right. And so when we're looking at these, we can tell what state of matter a substance is based off of the little symbol we have that's going to be written as a subscript beside that compound. Okay. Now, the next thing that we can see in a reaction is that some reactions to occur, we're going to have to actually heat them up or cool them down. And so what we can see is that a change in heat occurred. That triangle stands for change. So we have that change in heat that can occur. Some reactions also require what we call a catalyst. Now, a catalyst is going to be anything that's going to speed up the reaction by lowering what we call activation energy. In biology, we talked about catalysts in that, like, for instance, when your saliva, when you're chewing food, there's enzymes in there. Those enzymes are biological catalysts. And what they're doing is they're breaking down that food. Why? They are speeding up the reaction, causing that food to break down, decompose into its base parts. Okay? Now, to signify that, we would say, okay, I've got my yield symbol, and the catalyst would actually be written over the top of it. So if I had MnO4 being used as my catalyst, then that would be how I signify it in the reaction. The very last thing that we can see is that I've got a substance and it is dissolved in water. And so this would be like salt water or actually rubbing alcohol. What we see is that those substances have been created by dissolving them in distilled water. And that's what we call a water solution. We call it aqueous. And so aqueous solutions we would signify by using a AQ as our symbol. All right? So those would be all the symbols that you should see as a part of these chemical reactions. And if there is anything else that pops up, I will kind of go over it as a part of the lesson. All right? Now, moving on. So now that we know the parts of a chemical reaction, let's actually talk about how chemical reactions occur. So we have what's called the collision theory. And the collision theory is basically telling us how a chemical reaction will occur. So for the collision theory, for a reaction to occur, molecules must collide with enough energy to overcome the activation energy. Activation energy is the energy required for the reaction to start. 3, for a reaction to occur, the molecules must collide with the proper orientation. And then 4, the collision must meet both of those criteria for the reaction to occur. So basically what that says is that for a reaction to occur, molecules have to collide each other with the correct speed/force and correct angle as well. So if I've got two molecules and they collide and they bump at the wrong direction, they're not going to form a chemical reaction, even if they've got the right amount of energy. Or if I have them at lower energy and they collide at the right orientation, the right shape, the right angle, then what we would see is that reaction still does not occur. Versus if we have the correct speed, the correct orientation, they slam together, and then the chemical reaction occurs. That's what we call the collision theory. It's basically saying, okay, I've got all of these conditions being met. And so a lot of times people are like, okay, well, how do chemical reactions occur if you've got to meet the right amount of force and at the right angle? Well, that's because there's so many elements, so many compounds in a small area, because atoms and molecules and particles are so small that you can pack a lot of them in a very small space. And so those collisions can occur at the right force and the right orientation or angle, actually fairly commonly. And so just because there's a lot of them, you're more likely to see that collision occur for that chemical reaction to happen. All right? All right. So now we know how a chemical reaction will actually occur. So let's talk about the types of equations. So these equations are going to be what we would do to represent a reaction on a piece of paper, okay? So there's 3 types that we talk about in this class. There's the word equation, the skeleton equation, and then the balanced equation. So the word equation is basically just a description of the reaction. So it is the description of the reaction. And so an example of that would be during a lab, a student mixes 32.5 grams of sodium chloride with 92.5 grams of water to produce blah, right? And so they actually explain what's happening and they kind of go in detail to what's actually occurring. Now, that doesn't actually give you a true equation that you can work with. So what you would do is you would turn that into the skeleton equation, which basically is just going to tell us what is present. And so in the case of the example that I just gave, you would say NaCl plus H2O produces whatever they said, right? So NaCl plus H2O produces NaOH plus NaCl, right? Or HCl. So when we're looking at that, sorry, y'all, someone just walked into my room. So wanted to pause it real quick. So a skeleton equation is just going to show us what is present. So like I was saying, you've got that sodium chloride and water, and it will say they produce sodium hydroxide and hydrochloric acid or whatever, right? So we're taking those two things and we're creating it, but it's not really telling us how much of anything we've got. It's just saying I've got salt and water and it makes X and Y. Okay? So I call the skeleton equation the bare bones of a chemical equation. It's just telling us what is there. Okay? Last one we have is the balanced equation. So a balanced equation, I think, is the most detailed because it's going to tell us what is present and then how much or how many of everything there is. So this is what you typically think of with a chemical reaction, where you actually have to see, okay, well, there's 2 of the sodium chlorides, there's 1 of the water, and you just kind of build from there, okay? So it's telling us what is present and how many there are. Now, this is going to give us a ratio, and it's going to help us know, like if I've got sodium and chlorine, that we know that's a 1-to-1 ratio there, versus a part of the reaction, we could see, okay, well, there's 1 sodium chloride for every 1 water, okay? So it is going to be a very important thing for you to know how to balance that equation. So that is actually why we've got a lesson on balancing equations. So let's actually dive into balancing equations. Make sure you understand what is going on, and we will, I guess, move on from there. All right. So when we're balancing a equation, we do need to remember that all chemical reactions should follow the law of conservation of mass. And so that means that if you've got a certain number of compounds or elements to start, you need to end with that same number of elements of each type. Okay, so how to balance this? So I'm going to read through these really quickly, and then we'll actually talk through what to do for this. So step 1 would be to make the number of each element equal on both sides. We're going to do that by using coefficients. Remember, you should never, ever, 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 never change the subscript of a compound. Okay, never change the subscript of a compound. I cannot reiterate that enough. That is the most common mistake that students will try to make, is changing the subscripts. Do not change the subscripts. You can only change the coefficient. And the coefficient, it shows you right over here, it's the number that you put in the front. Do not change that. Okay, do not change the subscript. All right, next, when you are balancing your reaction, remember to balance your oxygen last. Keep your polyatomic ions together if they're on both sides. By that, I mean if I've got carbonate on the left and carbonate on the right, then I'm going to just keep it together. If there's carbonate on the left and carbon dioxide on the right, they are not the same, so I would need to break it apart into carbon and oxygen, okay? Next, we're going to use the lowest possible ratio of coefficients. So if I've got 2, 4, 2 as my coefficients, then really that should be 1, 2, 1 as the coefficients. Remember your diatomic elements. Remember those elements are always going to be found with 2. Okay, so like nitrogen, it's always N2 unless it's in a compound. Again, never change your subscripts. And then 8, never put a coefficient in the middle. So you see what they did right here? So here I put the coefficient at the front. That tells me I've got 2 sodium and 2 chlorine. Versus here, this is just wrong. Okay? So you should never put that coefficient in the middle of that formula. So those are your rules. So let's actually get down and look at how to balance an equation. So I personally like to line everything up. So here I've got aluminum and oxygen. And I am basically saying, okay, on the left and on the right side, I should have aluminum and oxygen. I should never see an element on the left and it not be on the right. So I shouldn't have like plus nitrogen here because there's no nitrogen on the left side, on that reactant side. And so that should not ever be there. If you've got an element on the left, it should also be on the right. So now I need to balance this. So on the left side, I've got 1 aluminum. On the right side, I've got 2 aluminum. On the left side, I've got 2 oxygen. On the right side, I've got 3. Okay. So remember the rule to always balance your oxygen last. And so in this case, we're going to start with aluminum because it's not oxygen. So how do I balance it? Well, we're going to use coefficients. Now, coefficients are multipliers. So comparing my 2 aluminum here, the ones on the left and the ones on the right, I've got 1 on the left and 2 on the right. So what that tells me is that I need to multiply the left side by 2, right? So I'm going to have to double that. So that's going to give me 2 aluminum, okay? So since I did that, what I need to do is come back up here and put a coefficient of 2 in front of aluminum. And that's going to apply to everything in front of it, okay? Next, my oxygen. Well, let's look at my oxygen. On the left side, I've got 2. On the right side, I've got 3. Remember, I'm working with multipliers, so I'm going to have to multiply by something. Well, is there something that I can multiply? A whole number I can multiply this oxygen by to make it equal 3. No, there's not. But there is a common number, a common factor that both of these go into. So we're going to multiply that side by 3. That's going to give us 6. So we'll put a 3 right here. And then we're going to multiply this side by 2, which turns that into 6, right? Which means we need to come back up here and put a 2 in front of that oxygen there. But what else did that change? Well, it also changed your aluminum, right? So you're going to have to come back and multiply that aluminum by 2. Okay. I suggest that you always start back at the top and work your way down, counting to make sure that everything is still matched up. Now, so I did my oxygen. It changed those to 6 and 6. So up here at aluminum, it was also changed, right? So my aluminum on the left, there's 2, and on the right, there's 4. Are they still balanced? No. So what that tells me is that I cannot multiply by 2. I'm actually going to have to change this to something else. So I have 1 aluminum. What do I multiply it by to get that 4? Well, I'm going to multiply it by 4. So then I have 4 aluminum. And I'll come up here and I'll put a coefficient of 4 there. So now I can compare my aluminum. I've got 4 aluminum, 4 aluminum. I've got 6 oxygen, 6 oxygen. Everything is balanced. I've gone in and I've put all my coefficients in. So then this would be my balanced chemical equation. Okay. So I'm going to do another one. We're going to work through this. Now this one, if you see, you've got 4 elements that you're working with here. And so we're going to work through this, and then I'm going to actually do another one with the polyatomic ions, and then I'm probably going to send y'all off to do the work on your own. All right. So here I've got Fe, S, H, and Cl. Those are the 4 elements I have. Fe, S, H, and Cl. And what I'm going to go through and do is label how many of each thing I've got. So on the left side, I've got 1 iron. On the right side, I've got 1 iron. On the left side, I've got 1 sulfur. On the right side, I've got 1 sulfur. Left, there's 1 hydrogen. Right, there's 2 hydrogen. Left, there's 1 chlorine. Right, there's 2 chlorine. Okay. So, first off, is it balanced? Well, no, because everything doesn't match up. So, we need to start at the top and work our way down. First off, do my iron match up? Yes, they do. So it's already balanced there. Do my sulfur? Yes, they do. Good there. Do my hydrogen? No, they do not. So I'm going to have to go in and multiply my hydrogen over here by 2. Puts a 2 right there. Now, since I did that, I find my hydrogen on the left and I multiply it by 2. All right. Now, when I put that coefficient there, did it change anything else? It changes my hydrogen, but it also changes my chlorine. So I have to come back and multiply my chlorine by 2. So that gives me 2 chlorine. Okay. Now I did make a change, so I always go back to the top and count back down, make sure everything is still balanced. So on the left side, on my iron, they are both balanced out. We've got 1 and 1. Sulfur, we've got 1 and 1. Hydrogen, we've got 2 and 2. And then chlorine, we've got 2 and 2. So everything there is balanced out. So this would be our balanced chemical equation. Now, one thing I do want to remind y'all of is that you do not put coefficients of 1. Do not put a coefficient of 1 in those blanks. Just leave it blank. We obviously know that there's one of them there if I wrote the substance there, right? So we do not put the coefficient of 1 in those places. All right. So I'm going to do one more, and then I'm going to have y'all do the next 2 as practice. So I've got zinc. Now, here's the thing. This right here is a polyatomic ion, right? And we know that polyatomic ions, if they are on both sides, can be used as a single unit. And by single unit would be, I would put O and H like that. Okay? So do I have it on both sides? Well, on the left side, I've got hydroxide. On the right side, do I have it? Well, I'm not seeing it, but water is actually HOH, right? HOH. And so from that, I can see that there is a hydroxide on the left and on the right. Okay? Next, I've got hydrogen. Is it on the left and on the right? Well, hydrogen right there and hydrogen right there. So yes, it's on the left and it's on the right. So we can leave it there. And then the last thing I have is the polyatomic ion phosphate. Is it on the left and on the right? Yes, it is. We've got it right here and we've got it right here. So it is in both places. It is on both sides, so I can write it as a single unit. All right. I'm going to rewrite that HOH over here just to make it a little easier to see. Okay, so now I need to go back in and try to balance this. So I've got 1 zinc on the left and 3 on the right. I've got 2 hydroxide on the left, 1 on the right. I've got 3 hydrogen on the left, 1 on the right. And I've got 1 phosphate on the left and 2 on the right. Now we go in and balance. So at the top, I start with my zinc. I have 1 zinc on the left and 3 on the right. So they are not balanced out, so I'm going to have to multiply my left side by 3. Yeah, it gives me 3. And that means I need to go back in and put my coefficient in front of the zinc. So there, I've done it. Now, does that change anything else? We changed our zinc, but we also changed our hydroxide. So we do need to multiply our hydroxide by 3 as well. So now I've got 6 hydroxide there. Okay. So moving on. So my zincs are good now. Let's move down to our hydroxides. On the left side, I've got 6. On the right side, I've got 1. So I am going to need to multiply my right side by 6, which gives us 6 there. We put a 6 in front of that hydroxide. Does that change anything else? Well, yes, it does. It also changes our hydrogens. So we're going to do that right there. Okay. Anytime I make a change, I always go back to the top and work my way down. On the left side and the right side, do my zincs match? Yes, they do. On the left side and the right side, do my hydroxides match? Yes, they do. On the left side and the right side, do my hydrogens match? No, they do not. On the left, I've got 3. On the right, I've got 6. So I need to multiply my left side by 2. and that gives us a total of 6. And we come back up here and we put a 2 in front of that hydrogen. Now, does that change anything else? Yes, it does. It also changes our phosphate. So we're going to multiply that phosphate by 2 as well. That's going to give us 2 there. I did make a change, so let's go back up to the top and check. Zinc didn't change. We got 3 and 3. They are good. Hydroxide didn't change. 6 and 6. It is good. Hydrogen didn't change. 6. Well, it did change. We changed it just then. 6 and 6. They are good. Phosphate, we've got 2 on the left, 2 on the right. It is also good. So, is everything balanced now? Yes, it is. So this would be our balanced chemical equation. So what I want y'all to do now is to go and solve the next 2 problems. Put your coefficients, pause your video, work through them, and then I will show you the answer for the coefficients of those after you have done that. Okay? All right, so pause your video. All right, so y'all should have had 1, 2, 1, 2 for the coefficients for that first one that I sent y'all off to work on, that SiO2, that silicon dioxide, and magnesium there. So I've got SiO2 plus 2 Mg produces Si plus 2 MgO. For the next one, we have 2 C2H6 plus 7O2 produces 4 CO2 plus 6 H2O. And that would be what we get. The very last one I am going to work with y'all is going to be one where you actually have to write out the chemical equation for this. So I've got carbonic acid, and they tell us it decomposes into carbon dioxide and water. So carbonic acid is H2CO3, and it decomposes. Decomposes is just telling us that it's going to be breaking down into smaller pieces, just like food decomposes, or twigs decompose in the woods or whatever. So I've got that. It's decomposing into CO2 and H2O. Okay? Then I would make sure to go in and balance. I've got hydrogen, carbon, and oxygen. There are 2 hydrogen on the left, 2 on the right. There is 1 carbon on the left, 1 on the right. And then there's 3 oxygen on the left, and then there's 2 plus the 1 here. So there's 3 oxygen on the right. So that is actually already balanced after writing that equation. Okay. All right. I want y'all to do this last one on your own. I am going to go ahead and end the video, but you can check the key to see if your answer is correct. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.